In this video, we're going to be talking about complex power, which is a new concept, and it's a very useful concept. Complex power, it's a way to keep track of the two types of power we had talked about in earlier videos. When we have a circuit where we are looking at currents that are coming in as I of t equal to Im cosine of omega t plus theta I, and then we have v of t as v of m cosine omega t plus theta v, and we are interested in the steady state character of the signal. Then complex power plays a very important role for us. Just a quick note before we go on. Im is the maximum current, Vm is the maximum voltage, and if you recall earlier we had a video that talked about I effective, or another name for it was I RMS, which was basically the value of Im divided by square root of 2. It's the root mean square average, if you want to think about it that way. And then of course we would have one for V effective as well. V effective is equal to V, it's another name for it is VRMS. I probably should write them all in capital letter. That's a common way people do RMS, because that's a abbreviation for root mean squared. And then that will be a VM divided by square root of 2. So that's correct. So now we have those two concepts. So now if you want to kind of find the power, is V times I to find the instantaneous power. As we talked about earlier, there are two powers that are really kind of important to us. One is the power with shown with capital P, and it's called true power, average power, real power. That it's one of those things with lots of names, but most of the time in our conversations we call it average power, or we may refer to it as also real or true power. And as we had discussed earlier, P is going to be basically, there's multiple way of writing it. I can write it as Im Vm divided by 2 times cosine of theta V, the shift for voltage, minus the theta I, the shift for current. Okay, and then we can take this 2, break it up to square root of 2, that we would have Im over square root of 2, Vm over square root of 2. Taking advantage of here, sometime you also will see this written as I effective V effective cosine of theta V minus theta I. Okay, so you'll see them written both ways. So that was the real. And you remember that the units, we refer to the units as watts. Okay, sometimes you can even think about this as being resistive power, if you like to think about it that way. And then we have the other one, which is mostly the reactive power. You can think about the power that's stored in capacitors, inductors, and things of that nature. And that's usually represented by a Q, and it's referred to as reactive power. Okay. And the reactive power, again, is pretty much the same idea. Im Vm divided by 2 and sine theta V minus theta I. And that becomes, again, we can write it in terms of RMS value or effective value. We can write it as effective V effective sine of theta V minus theta I. So now we have that. And complex power is just a way for us to be able to represent both of these powers in both P and Q in a way, in one equation that we could use maybe with the phasor domain knowledge that we have, and be able to write equations that are more simplified instead of having to have a separate variable for P, another place for Q, keep track of those things. So this, they write it as S, the variable they used to, character they used to indicate complex power is S. And what they do is S is equal to P, the real part, plus JQ, the reactive part, okay? And then remember, I forgot to put this in here, but the Q is volt amp reactive, and this quantity together, the units, so the units for S is volt amp. That's how they refer to it. Now, just a little bit of a comment going back and thinking about complex powers, complex numbers. If you recall, complex numbers are drawn on an axis when you draw them. That here is the real axis, okay? And here is the imaginary axis. And then so if that's the case, then the S would be, this will be the vector S, or the complex number S. And if we kind of draw a perpendicular line to this axis, this portion would be, which is over here as well, I suppose, is Q, the imaginary part or the reactive part, and this piece would be P. Okay, so and then we can apply all, and then we have the theta. Okay, so and we can apply all the complex numbers and conversion that we have learned so far to this complex power too. So let's take a minute and kind of go through that, so we've kind of seen some things. The magnitude of this is referred to as a apparent power. So the magnitude, which we usually write this way, is referred to the apparent power. An apparent power is the square root of P squared plus Q squared. And so now we know the apparent power. Theta is kind of interesting. So if you think about what theta is going to be equal to arctangent, or tangent for convenience, I'll write it as tangent inverse. But this is arctangent of imaginary over real, right? The tangent of theta is this front axis, which is imaginary over the real. So you can also write it as tangent inverse of Q over P. One other interesting observation to have is that the phase angle for complex power is going to be Q divided by P, which is going to be sine of theta V over cosine of theta V theta I. So another way to think about this, the tangent inverse of that then would be theta V minus theta I. That's kind of an interesting thing to know. So the phase angle of complex power is theta V minus theta I. Okay. So that's kind of interesting. If you remember, we called this power factor angle, right? So this is power factor angle. So if that's a power factor angle, then really interesting. So this is also then power factor angle. So the phase of a complex power is power factor angle. So therefore, if somebody wants to find a power factor, all they have to do is just take a cosine of theta of the power, and they're done. So when also we can think about this as being, if somebody wants to find it, somebody gives us complex power and asks us to find a power factor, we can say, oh, okay, so that is gonna be P, the side, divided by magnitude or apparent power, and that's another way of getting it. So that, as you can see, these are all interrelated to each other as we go and deal with this. So I think that's a good place to stop at introducing complex power, and we'll come back, and in future videos we'll take a look at how complex power could be related back into V effective, I effective, and all of that.